Nitrogen. It was a dark and rainy evening. It was the 19th century. That means the 1800s. Sir William Crookes is set to give a speech to the Royal Society in England. The room was smoky. There was tense music in the background. Sir Crookes, he didn't like his name very much, outlined what he thought were the gravest threats to society. At the top of the list, fertilizer. Well, fertilizer to grow food, to be specific. Actually, people knew enough about fertilizer at this point to know that it was actually the nitrogen in fertilizer that we needed. Nitrogen and some other nutrients that were in it. We actually need nitrogen in a specific form in the soil in order to make plants thrive. This is called fixed nitrogen. Yes, there is going to be more about fixed nitrogen later on. Stepping back a little, throughout the 19th century, the demand for nitrogen had been steadily increasing. As farming methods became more sophisticated and people realized they needed nitrogen, or fertilizer, the demand kept increasing. Now, people were starting to get worried about it, including Sir Crookes. The worry was that the population would soon exceed the food production capabilities if everything stayed at the current levels. Therefore, people started a worldwide scientific industrial search for alternative sources of nitrogen. Fixed nitrogen, to be exact. Why is nitrogen such a big deal? Well, for one thing, your body and everybody else's bodies has about 5% nitrogen. 5% doesn't seem like a whole lot, but let's look at a couple of things that nitrogen is in to see just how critical that nitrogen is. So the number may seem a little bit small, but nitrogen is contained in DNA, RNA, and proteins. Every protein, all DNA have nitrogen. It's pretty important. It's kind of a big deal. What, you don't believe me? Well, how about this? See this picture? This shows you that nitrogen is contained in protein backbones. See that thing right there? Yeah. That little chain is the backbone of all proteins. All proteins have these things called peptide bonds, and they are a nitrogen bonded to a carbon. So the chain goes nitrogen, carbon, carbon, nitrogen, carbon, carbon, nitrogen, carbon, carbon, etc., etc. Every protein in your body needs nitrogen. Your body, the structural elements of your body, the enzymes, just about everything is made of proteins. That is a picture of one side of a DNA chain. You see these things labeled purine and pyrimidine bases? They have adenine, guanine, cytosine, and thymine. If you look at those side groups, you'll notice that every single one of those groups has a nitrogen, 2, 3, or 4 nitrogens in those adenine, guanine, cytosine, thymine side groups in DNA. Yeah, that's right. DNA has side groups. They're also sometimes called bases. That's in a chemical sense. These groups are called adenine, thymine, guanine, cytosine. They're sometimes just abbreviated to their first initial, ATCG, and they are actually the pieces that hold together the twirled up double strand of DNA that you may have seen pictures of. They are also the code that the DNA and RNA use to create proteins. Computer code uses bits that we sometimes think of as ones or zeros. So computer code has only 2 different letters. DNA has 4. So these ATCGs are kind of like the zeros and the ones in a computer. So every protein and all DNA have nitrogens that are absolutely critical to the structures that are in them, the molecular structures that make them up. This means that the nitrogen is pretty important in your body. And not only this, but since proteins and DNA are common to all life, then all life needs nitrogens. They get it from wherever they can. Wait a minute. I just got an idea. See this air around us? It has nitrogen in it. In fact, it's 70% nitrogen. There's a lot of air out here. That means that we are literally surrounded by nitrogen. Literally. There's a lot of nitrogen. What's the big deal? Why can't we just take the nitrogen from the atmosphere? That's a good question. It turns out that the nitrogen that we need is a little bit different than the nitrogen that's in the air. The nitrogen that's in the air is a nitrogen bonded to another nitrogen with a triple bond. That triple bond is super strong. It's like chained together with this incredibly strong force that won't let it break out under normal circumstances. How are we going to get that nitrogen from the atmosphere and put it into a usable form? That is the question. This process is called fixing nitrogen. The picture that you see here is a representation of the nitrogen molecule. This shows a Lewis structure where lines represent bonds and dots represent individual electrons. You can see each nitrogen has 2 electrons on one side, we call those lone pairs, and then 3 bonds to the other nitrogen. In order to be usable by plants and animals, we need the nitrogen to be just either a single or a double bond to something else, something that we can actually use and incorporate into our bodies. The 3 bonds in the molecular nitrogen in the air are kind of like strong chains holding it together, making it so that we can't use it. It also makes nitrogen very non-reactive. It doesn't want to participate in many reactions. This is probably a good thing. Since it makes up 90% of our atmosphere, the low reactivity kind of makes the atmosphere low reactive. Probably a good thing for us. So I think we've done a good job outlining the problem, which is that we need to get nitrogen from the air, but it has these really strong bonds. If that's the case, how does anything get nitrogen and use it? Well, for one thing, all right, let's give due here. Lightning. Lightning shoots through the atmosphere with so much energy that it actually breaks apart some of these nitrogens. So after a lightning strike, the lightning creates some usable amount of nitrogen in the atmosphere around, and that can then settle to the ground. The primary component made by lightning is nitric oxide. This is where a nitrogen bonds to an oxygen atom. Since oxygen is the second most common component in the atmosphere, that kind of makes sense. Since lightning gets hotter than the surface of the sun, I guess it has enough energy to break those really strong bonds holding nitrogen together. This doesn't completely solve our problem though. Unless we want the entire surface of the earth to be constantly hit by lightning strikes, we don't have enough lightning to make as much nitrogen as we need. There are some other natural sources of fixed nitrogen. Certain bacteria can actually take nitrogen and turn it into a usable form. There are plants that actually have symbiotic relationships with these bacteria, and they both work together in a win-win situation where the bacteria produces nitrogen that the plant can then use. Some of the plants that generate nitrogen are using this very process. These bacteria have a special protein called nitrogenase. Nitrogenase is an enzyme that produces usable forms of nitrogen from molecular nitrogen. An enzyme is something that speeds up reactions in a way. In this case, nitrogenase is what allows these bacteria to take nitrogen in a molecular form and break it and put it into a usable form. These bacteria mainly reside in the roots of certain plants like legumes. If you've ever heard of the farming technique where you rotate crops and you substitute in things like legumes or beans sometimes, those legumes are there to generate additional nitrogen in the soil. So you take a break from the regular crops, you put something that's going to grow some nitrogen, you can maybe make a little bit of money from it, and then you sort of replenish your soil with nitrogen. This method of fertilization is still used sometimes. All right. Getting down to the traditional method of putting nitrogen in your soil, cow manure. Cow manure has been used since time immemorial. I should say manure from animals in general. This was a great cycle for us. We have some animals, we feed them, they do their business on the ground, we take that, it fertilizes our crops, we get more food that we need, and then we can also even sometimes eat those animals too. Shh, don't tell them. There is, practically speaking, a limit to how much food can be grown this way. This is why people were worried in the middle of the 19th century, roughly, that we weren't going to be able to make enough food for the population as it was growing. So we know we need more nitrogen. People had figured out that manure wasn't what was needed. It was actually the nitrogen in the manure. And people had found at least some alternative sources of nitrogen. Here's the problem with these sources. Saltpeter was the main form of nitrogen that people had found. Saltpeter is a naturally occurring mineral. In some areas of the world, people have saltpeter deposits. They can just go literally pick it up or dig it out of the ground. Here you can see the structure of saltpeter. See that nitrogen? It does not have a triple bond to anything. Therefore, we can use that form of nitrogen in our bodies. So what people did, they just added some saltpeter to their fields, and this acted as an artificial fertilizer. Great. All we gotta do is get some more saltpeter. Let's go get it. Saltpeter was mainly in the country of Chile. Chile had large amounts of natural deposits of saltpeter. Chile was the only country that was known at the time to contain large amounts of these deposits. So they were the only game in town. If you wanted saltpeter, you had to go there. This sort of monopoly is not a recipe for a good functional system. Why? Because people start to realize that they're the only source. Chile had a cash cow in saltpeter. The problem is that the resources that Chile had were themselves dwindling, and they also had a little bit of a situation going on. Here's how Wikipedia puts it. In 1900, Chile, with its deposits of saltpeter, produced 2/3 of all fertilizer on the planet. However, these deposits rapidly diminished. The industry was dominated by an oligopoly, and the cost of saltpeter rose constantly. To ensure food security for Europe's growing population, it was essential that a new economical and reliable method of obtaining ammonia be developed. Ammonia is a usable form of nitrogen that is useful for fertilization. Ammonia has a chemical formula of N with 3 hydrogens attached to it. So you get the picture. We have a form of artificial fertilizer that we can use, but its prices keep going up. It looks like it's going to eventually just go away, and at the same time the population is increasing. This is a real problem. What was really needed was a mass production technique. The guys who would eventually win this race were named Fritz Haber, who was a chemist working on this problem, and a chemical engineer by the name of Carl Bosch. They found a way to economically produce ammonia. What they really did was find a catalyst that would work in the production, and they formed this catalyst and were able to use it in a high temperature, high pressure industrial technique. The method they were using was actually pretty expensive to do, but you could sort of turn it on and sort of leave it running, and the costs would be minimized in that way. The reaction that formed it is shown here. Whoa, 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 whoa. Did you see that? The reaction formula. It had energy on the right-hand side. Do you know what that means? This is an exothermic process. That means it gives off heat to the external environment. What? Why, you might ask, is it difficult to break apart nitrogen if when I do that, I literally give off extra heat to the outside? That is a great question, and I am glad that you noticed it and asked it. If you will, take a look at this energy diagram shown below. You see that 1129 kilojoules per mole jump? That, my friends, is called the barrier energy. Somehow we have to put that much energy in order for the reaction to proceed. After the reaction goes, it actually overall gives off a little energy, but that huge energy barrier must be gotten over somehow. This picture that you see here is actually a look at the catalyzed process to get through it. Without catalyzing this process, we have a very difficult barrier to get over. So Fritz Haber and Carl Bosch figured out how to make this a doable, workable solution. The process was still energy intensive, but it was still economically feasible. This process that they discovered has fed millions, if not billions of people. It is hard to overestimate how important this reaction has been to modern society. Well, they did it. They figured it out. And now science has solved this incredibly difficult problem. And now everybody has enough to eat. And we're all going to get along thanks to our savior, science. Yay! You might think Fritz Haber would live a happy, successful life, secure in the knowledge that he was wealthy and also that he had helped secure food for the surrounding populations of the world. There are all kinds of interesting personal aspects to Fritz Haber's life. For example, he helped the Germans develop and use chemical weapons in the First World War. After this, his first wife committed suicide, possibly from the guilt associated with his work on chemical warfare. Also, fixed nitrogen just happens to be needed for making most explosives. So his process of fixing nitrogen would later help the Nazis' war effort in World War II. Fritz Haber, who was Jewish, saw himself as a good patriotic German, but eventually his position became untenable as the Nazis rose to power. Perhaps mercifully, he died in 1934 before the full scope of Nazi atrocities could be revealed. This is the personal side of Fritz Haber, and that we see in science and technology in general. Nothing happens in a vacuum, and in this case, the personal side is a little bit more of a tragedy. Fast forward after World War II, and in the 1960s, several groups would lead something called the Green Revolution. This taught farmers in poor countries how to use artificial fertilizers and use modern farming techniques. This movement would drastically increase crop yields in these countries, and it all goes back to the process developed by Haber. In more modern times, some have criticized the dependence on modern farming techniques using chemical fertilizers. The nitrogen is washed off of fields and can contaminate surrounding land and water. Over-fertilization could be the culprit, but folks are still studying it. Finally, let's look to the future. We have a method of mass-producing nitrogen to our heart's content. So we're good, right? What work does that leave you? Well, the Haber-Bosch process requires a lot of energy input. What if we found an alternative way of generating nitrogen, more similar to what bacteria themselves are actually doing? This leaves just a window open for possible work in this area, and there's lots of other work that can be done in chemistry in general. Perhaps you can help fix that problem.